let me know whether you can hear me as I share my screen. Yes, anybody that can hear me?
Yes, we can.
Okay, perfect. So let's pick up from where we left, and we were winding up on the read-only memories, and we were to look at the application of the read-only memories. So one, Moses, how do people join such that I don't need to admit them? How should they join?
For this one, you might be forced to. Maybe you could have created the invitation link for
So sorry, I
the
can't hear you well.
I'm saying maybe you could have created the invitation link. I'll share with you the emails you invite us via the emails. So next time we won't have the option to admit us. Other than that, maybe you open the meeting, you make the meeting open for everyone.
Um, okay, anyway, we'll talk later about that. So yes, one of the areas where we have read-only memories used, and of course this is very common. And remember, there is a whole range of what we categorize as read-only memories. Starting from the mask, uh, the programmable ROM, all the way to the flash memories. So one is in the area of the data transfer. Data transfer and portability. And so we'll just be highlighting. We don't need to spend much time here. So here you have your USB drives, um, especially for portability. You also have electronics such as what do you call them? Cell phones. You have the digital cameras, and in this you'll find that they make use of the removable storage media such as the SD cards, which are in essence flash memories. So generally, you will find that these electronics that are mostly um, battery powered, they will make use of flash memories. So and what's the reason for that? The characteristics of flash memory that that make this favorable. One, we know they are low power as well as low cost, and we said that they also have a high density, so you can get gigabytes of storage in a very small area, and of course they are also non-volatile, so they will not lose any data on being powered off. And also these are there is the in-circuit programmability or write capability. So those are some of the characteristics that make flash memory widely used in such devices which are mostly battery powered. The other area that you will find read-only memories being utilized are in bootstrap as bootstrap memories. And this, when we talk of bootstrap, we are talking about the booting up process in computer systems. So this is in computer booting. And I think one of such programs that has been in existence for quite some time is the BIOS. So here we are talking of, remember the BIOS in itself is a program. And where is that program stored? It is stored in a read-only memory, because it actually comes, you know, from the manufacturer. So this, and we know what the BIOS does. This is, it enables or performs the startup procedures when the computer boots, and so forth. So in computers, we have such a program BIOS stored in a read-only memory. Also, in the world of programmable logic devices, for example, FPGAs. So in programmable logic devices, for example, FPGAs, will find read-only memories being used to store the configuration information for the device. So we can note that, sorry, we can note that, for example, FPGAs, they will load their programming information which configures their logic circuit, which configures, and when we talk of the programming information, remember here it is hardware programming, and not the software programming as we know it. And when we talk of the hardware programming, you are actually configuring circuits at the hardware level. um, you know so um, so they will load that programming information from an from external read-only memory into a random access memory area, which now is inside the PLD, in this case inside the FPGA. Um, Still in bootstrap memories, when we come to the world of embedded systems, we'll find so in embedded systems, we'll not talk of the BIOS, but the bootloaders. Now, these automation will be becoming a lot, but hopefully next time we'll have a better way of people joining without the need for this admission. So in the world of embedded systems, we have the bootloaders and examples here. We have the U-boot, a very common bootloader in embedded systems. And this uh, the U-boot program contains the instructions to boot the device's operating system kernel. So you'll find that, for example, the OS itself might be stored in an SD card or in other memories, and now the U-boot will facilitate that booting up process, including selecting the device or the memory device from which the OS is stored. So such a U-boot program will load the operating system from various memory devices. For example, those memory devices could be from an SD card, could be from an embedded multimedia card. Yeah. So these are some of the areas that we find ROM memories being utilized in. So we have talked of the data transfer and portability, and also bootstrapping. This includes in computers, in programmable logic devices, and also in embedded systems. Then, so not only bootstrapping, but also the main memory or the program memory itself. So we'll find such usage in controllers, and this is for program memory. And in such devices, we have the flash memory, and this is where the program instructions, the main program instructions, are stored. So the flash memory is used to store the microcontroller, the microcontroller program instructions. And a flash memory, of course, is one of the key specifications of an MCU. So you may decide to choose one MCU over another one because of the available flash memory. You may find that the kind of program you want to run or to write for that system might not fit in a particular MCU because of the flash memory. So this is a key consideration when developing solutions around MCUs. You want some sufficient flash memories. Also in MCUs, you will find the use of the EEPROMs. For example, this is for storing long-term information, for storing long-term information. For example, maybe configurations, some configuration data, also passwords. You have some system, and somebody has to log in. We are talking of systems that are offline, so even those passwords and login credentials are locally stored, and the EEPROM would be a very good solution for storing such information. Um, yeah, so I think, yeah, those are the application areas. Then maybe the other application area that we can look at, and the last one for us, not that there aren't other application areas, but we have just listed three, and now we can also look at the fourth one. This is on data tables. And when we talk of data tables, here we mean storing of data that doesn't really change. So these data tables, this is storage of store tables of data that doesn't change. And such data, for example, would be the trigonometric tables. So this, for example, if it's the sine, the cosine, and so forth, those are more or less circumstances. So it doesn't change. So for example, in calculate, if you were to have the CPU at any given query always computing things, even for those that really do not change, um, you know that would be probably inefficient. But I can imagine that probably a calculator, we have these lookup tables that if I'm keying in the the sine of 30 degrees or the cosine of 65, you know, we don't need CPU time for that, because we can store the results in a tabular form, and therefore it's just a matter of reading reading off that value, instead of doing some mathematical or arithmetic operations. So you just look up, or the CPU will just look up uh, the value from a table and continue with the other mathematical calculations. So that is a very common use of read-only memories. So this is for lookup lookup tables. So solutions are stored in a tabular form, and you just read them out. Uh, Also, under the data tables, we can also store mathematical functions. We can also store mathematical functions. So this is just similar to that lookup table kind of thing. That instead of always the CPU kind of in the first principles, it already has the results and just read them. So, for example, when we talk of storing mathematical functions, let's say we have such a function. Um, we have such a function, x squared plus 3. Of course, our variable here is x, yeah. So that x can be any number, and then you feed it into that mathematical function, and then you can get the value of y. So what if you these are pre-calculated for any given value of x, probably within a range, and stored in a table. Yeah, so that makes such mathematical function operations very fast. For a calculator of very limited, CPU and DSP resources. So this one we will store in a table, and in this case, the table should show the desired output. The table should show the desired output for each set of inputs. In our case, the input here would be x. So how can we use ROM memory to actually store that kind of data. Yes. So let's say there was somebody who was joining, but I think he has disappeared. So how would we store this kind of mathematical function in using some ROM memory? Okay. So let's say our x, and this is based on that mathematical function we have there. Let's say, of course, as I have said, that x can be anything, but for simplicity, in terms of us demonstrating, can limit the, you know, what this x, the range of x, what x can be. So if x is maybe is limited to the range of of 0 to 3. So we want to store the value of y for the case where x is 0, x is 1, x is 2, x is 3, just for illustration purpose. Remember, we are talking of storing those that value of y in a ROM, in a read-only memory. For example, in the mass-programmed ROM, MROM, which is done at the manufacturer point. And remember, when you talk of a memory, we are talking of the memory cells being individual transistors or individual MOSFETs. So we can either store a 0 or a 1 in that memory cell. So it kind of looks very straightforward. Like if I want to store the value of y when x is 0, it will just be y equals 3. But how do you actually store a 3 where you can only store a 0 or a 1? So that's where the a little bit deeper introspection comes in. That it looks very straightforward. That if I want to store the value of when x equals 2, it will be 2 squared, which is 4, plus 3, which is 7. So y equals 7. So I just store y equals 7. But now I'm storing in a medium that just allows me to store a 0 or a 1, just a single bit, and not a decimal number in its raw decimal format. So how do we approach that? So in such a case, and this is for illustration purposes, x, we take our input, the input a binary number x, the input binary number x to be represented by addresses A1 and A0. So in that case, we have our input x. So we are doing this, for the case of the range of 0 to 3. That means, in essence, our x is limited to just 2 bits. So it's a 2-bit number, A1, A0. And then, so that means this number can be 0, 0, can be 0, 1. Use a different color. It can be 0, 0, can be 0, 1, can be 1, 0, can be 1, 1. And then what will our output be? Our output, what will our output be? In this case, our output is y. And how do we get y? Y is x squared plus 3, based on our example. So where we have limited our x to be in the range of 0 to 3, that is just 2 bits. What will be the range of y? What will be the range of y? Somebody? If we limit our input x to be in the range of 0 to 3, what will be the range of y? Sorry? Yes, so somebody is saying 3 to 12. Of course, yeah, so 0 squared plus 3 is 3. So that's the minimum value of y. And for this range of x, then the maximum will be 3 squared, that is 9, 9 plus 3, so that is 12. So if we have a maximum possible value of 12, how many bits do we need for y? Somebody? How many bits do we need to store y?
4.
4.
Okay, yes, thank you. That's very correct. So our y will need 4 bits. So those 4 bits we can label them as such. Yeah. Remember, this is just for illustration purposes. Of course, at the manufacturer level, probably that value of x, could be as big as probably what makes sense as far as the memory is concerned. But for illustration purposes, we're just using this. So so when x is 0, y is 3. So how would we represent that in a binary form? This one would be, can somebody give me starting with the most significant bit? For the first case, when x equals 0.
0, 0, 1, 1.
Yes, correct. So this will be 0, 0, 1, 1. For the second, where we have now x is 1, so that one will be 1 plus 3, which is 4. In binary, what would that be?
0100.
Yes, correct. This will be 0, 1, 0, 0. Next one, x now is 2.
0111.
Yes, correct. So that will be 7, 0, 1, 1, 1. And finally, when we have x as 3, y will be 12. What is 12 in binary?
1100.
It's the correct 1, 1, 0, 0. So at least here we we have we have the results, the raw results, but now we are saying that this this value is pre-calculated and stored in memory, and this is it is achieved at, at manufacturing stage. By the use of various connections, the MOSFET connections in the memory. So if you recall this is what we talked about for the MROM. So how would we achieve this? How would we store this exact data in MROM? So to hasten things, I'd already started drawing the capturing, what do you call it? Capturing that memory structure. So we can finalize this together. So we want to store all the possible values of y, and in our case there are only 4 possible values because of our limited range of the input. How many values do we need to store in our MROM? Somebody? That is the results, the values of y that we need to store in MROM. Somebody? Yes? How many? I mean, we have already calculated the results here. How many values do we need to store of y? Is it 1, 2, 3, 4, 5, or how many?
4 values.
Is yeah, very correct. I mean, we just need to store these values. So this is one value. It's only that it is now in binary form. This is another value, the other value, and this value. So that means in our memory matrix, this value, which is a 4-bit word, can be stored in the first row. This other one in the second row, row 3, and row 4. So these are the memory locations. Yeah. So we are storing a 4-bit word. So each memory location will have the 4 transistors, and those are the ones that we have here. So we have these transistors. So that forms our first row, and then we have all these other transistors. I will not label all of them, but these are all the way to Q15. Yeah. So let me just complete this structure. If you recall, this is what we have already covered, but now we are showing how we can store some mathematical functions in a mask programmed ROM at the point of manufacture. Yeah, so we are making all those connections, and then this line, it goes all the way to the VDD. We have this going all the way to VDD. We recall our pull down resistors. So we also indicate them here. Then we have all our gates. Okay, so we're almost there. So where will these gates be connected to? What do you think these gates will be connected to? Yes. Remember, all the gates for each memory location are connected together. So for memory location 1, we have this line connecting the gates and so forth. So where would these lines be connected to? In other words, what would we use to select the various memory locations? Yes, anybody?
The input X.
The input X, but our input X only has two lines, A1 and A0, yet we have 4 memory locations. How would we connect the input X to those 4 memory locations? Anybody? So that we can finish on this. We have looked at this said before, unless you have switched off.
I use a decoder or what decoder.
Yes, yeah, very correct. Remember, we have already covered this. So in this case, we have, if we for the binary decoder, we need 4 outputs. We need 4 outputs, and we have 2 inputs, right? So we will need a 2x4 decoder. So we can illustrate that here. And then we have our 2 inputs, maybe a chip enable. So this is a 2x4 decoder. So at least now with this, if you want to find the value of, or to read the value of y, the output, when x is 0, then just 0, 0 is fed here, and that has the effect of selecting this memory location whose data will appear in these outputs. So these are our outputs: D3, D2, D1, D0. And recall how we said that the manufacturer's a stage, how they program these MOSFETs to either store a 1 or a 0. So for the first memory location, we want to store 0011. So for the bit, the most significant bit, D3, we want to store a 0. How do we do it? What do we do here in this Q0, MOSFET Q0? What do we do to store a 0? Yes, somebody?
store 0, we'll have to leave it open.
So we leave it open, that's correct. In D2, we also want to store a 0. What do we do? I suppose we leave it open. In D1, we want to store a 1. What do we do? Somebody? Yes?
Connect it.
Yes, so we'll make that connection. So here, we want to store a 1 in that memory location. So we make those connections. So that goes on for all the others. So for the second memory location, we want to store a 1 in D2. So we'll make a connection here. Remember, these are now permanent connections. You know, when this chip is being manufactured, then in memory location 3, we want to store a 1 in those 3 memory cells. That is here, there. Then finally, memory location 4, we want to store 1, 1. Yeah, and that's it. So this memory location stores a 0, 0, 1, 1. This stores a 0, 1, 0, 0. This stores a 0, 1, 1, 1. And this memory location stores a 1, 1, 0, 0. And in so doing, we have illustrated how indeed our mask programmed ROM can be used to store mathematical functions, you know, and that makes calculations very fast because there are no, you know, there are no, computing intensive tasks to be done. It's just reading off the values in that memory location, and then, addition is not, intensive. Therefore, that addition plus 3 can be done, and so forth. But in essence, this was just an illustration of how or why we are saying that ROM can also be used for data tables. That is either storing, for example, trigonometric tables or mathematical functions. And I hope this helps to drive that point home. So when we meet on Monday, we shall now commence on the random access memories. Yeah, so for now we can stop there, and we meet on Monday, unless there is any question. I will stop sharing. So if there is none, I think we can stop there. Let's meet on Monday.